We are starting the third week of our course, and now we will talk about phase transition finally. So, okay, so what we proved in the last 2 weeks can be summarized as follows. You have a connection between the pressure and the Gibbs measures, right? And you have that there exists the thermodynamic limit of the pressure. We saw this. Beta H. We saw a connection between the derivative of the pressure with respect to the magnetic field and the thermodynamic limit of measures, of local measures, for any boundary conditions beta H of the magnetization density. And this was valid every time the pressure was differentiable. And then we saw that we said that a first order phase transition, this is what it's called, phase transition, would happen when the first derivative of the pressure does not exist. And then we started our investigation of the Gibbs measures, right? And then we showed the following result that was important. We showed the existence of the thermodynamic limit of these expectations, beta H with plus boundary conditions. Beta H when for any local function, local, and this implies the existence of a measure on the configuration space such that this quantity is exactly the integral. This is the integral of this measure on the configuration space, okay? And the same, we saw the spin flip, the spin flip. The spin flip that is a map on the configurations that send sigma to minus sigma. And we saw a relation between the plus boundary condition measure and the minus boundary condition measure with respect to the spin flip. So you go to one and the other using the spin flip, but you also flip the field. So this implies, since this exists, this will imply also using the spin flip that the minus boundary condition probability measure will exist, the thermodynamic limit. And then we also show that when H is different from 0, the pressure is differentiable. Is differentiable. implying that this limit is always equal for any boundary condition. I gave, I think, as an exercise to show that this converges to the expectation at 0 in the thermodynamic limit, beta h. And since the pressure exists, this would imply that when h is different from 0 and uniform, then sigma 0 beta h is equals to sigma 0 minus beta h. And then this implies that there is a unique limiting Gibbs measure. So in order to search, to find actually, in order to find the phase transition phenomena in ferromagnetic easy spin systems, we actually need to explore what happens to the case h equals to 0. So notice first that in the case h equals to 0, then there is no, when you flip the field, when you change the sign of the field, you get the same thing. So what happens that the plus and the minus boundary condition are related by the spin flip symmetry, okay? This way, beta lambda beta a 0, okay, minus here. And if you take the limits, when you look to the expectation value at the 0 site, then this implies, by taking limits, that in order to not have a phase transition, I will not write the 0 of the magnetic field anymore. For now on, the field will be 0. Then this implies this relation right here. Okay. So in order to then to be equal, to guarantee the existence of the derivative of the pressure, this relation forces the value, this forces to not have phase transition, This forces the expectation value, this relation, this spin flip symmetry, this forces the expectation value to be 0. So in order to show phase transition, I will have to show that this doesn't happen at some regime of some parameter. And the parameter that we have, the only parameter that we have remaining here is the beta that is related to the temperature. So, okay. So let us see first what happens to a toy model, some easier set of configurations. And for first notice the following: I can write this expectation value for any lambda. I can write this as the expectation value of the characteristic function of this spin, taking the value plus 1 minus the characteristic function of the spin taking the value minus 1 beta plus. But since this is a probability measure, okay, I know that the sum of these two expectations is equals to 1. I also know that this is equals to 1. So what this means is that I can write the expectation of the spin 0 as 1 minus 2 times the expectation of this characteristic function. Okay, so in order to show that this is positive, for instance, what I want to show is that this is positive. So it's sufficient to show in order to show that this is positive, well, I can try to show that this happens. This is sufficient. Let's say it's less than 1/3 for any box. So if I show that there exists a beta, some beta star, let's say, such that for some regime of betas where there's a beta such that for any box I can show this, for any finite set I can show this, then this would imply, if I can show this, then this would imply that this quantity right here is uniformly bounded with respect to the box through 1/3, right? Then this is positive. And by the spin flip symmetry, this is minus here. By the spin flip symmetry, this would imply that the minus boundary condition would be bounded by minus 1/3, so it must be negative. So this implies that those two quantities are, in particular, this implies that they are not equal also. Okay, so what we will try to show is that at some regime of betas, this happens uniformly with respect to the box, to the finite set lambda. Okay, so first, let us see what happens to a very specific kind of configurations. Okay. Just to have a taste of what can happen. So consider omega b, okay, a subset of the configurations with plus boundary condition that are defined by the following. So for any sigma inside here, there will exist a set. There will exist a set C. There will exist a box, let's say CR. I'll write like this. So what is this? These are the points. These are the points. Let's say these are the points in ZD. Okay, such that x minus y is less than r, where this is the supremum norm. Yeah, this is the definition. Okay, so what are these? Okay, so there exists a box. Okay, such that first, so the box is inside lambda, and second, this is the first condition, and second, sigma x equals to -1 if x is inside the box. Sigma x and sigma y is +1 otherwise. So how these configurations look like? So if you have a finite set, here lambda, this is your lambda, then for sigma to be an element of this configuration space, then there needs to be a box. This is why I use this supremum norm, because the balls are boxes. There will be a box, CRX, okay, centered at X, in such a way that here I only have minus sign, and outside I have only plus signs. So this is so these configurations are easy because they only have a very nice geometric. They have nice forms, nice shapes. They are boxes. So okay. So what would happen if I tried to study So remember last week I used this notation right here for characteristic functions. I use this notation. I will now proceed to use this notation again. So what happens when I try to study this event, the event that I'm interested in, the event of sigma 0 being -1, okay? Conditioned to this configuration space. So my configurations are only allowed to vary in this set. So what happens is the following. So I can write this, remember, the definition of the conditional probability, okay? Omega b, and this gives us the sum 1 over probability omega b times the sum over all configurations inside omega b, such that the spin at the zero site is equals to -1 times the weight given by this. So, okay, now we don't have the magnetic field. Okay, so remember that the Ising Hamiltonian has this form. With respect to the plus boundary condition. It has this form, but there is a beta multiplying everything. So for now on, I will not write the beta over here. I will just write the beta here, because the beta is present in each term of the Hamiltonian. So I'll just write like this. Okay. It's nicer now. So and calculated at this configuration right here. Okay, what next? So I need to give an upper bound right here. So I don't have any control of what happens to the values of this energy right here. But there is an interesting phenomena happening right here. Is that this function here, the Hamiltonian, it will have a minimum. It will have a minimum value over all the configurations in the local configuration space. So these configurations that have some minimal value over here are known as ground states. So I will not dwell too much. I'll not say too much about the ground states, but there are many things to talk about this. But I will start to call the plus and the minus boundary conditions as ground states. And I'll not define precisely what this is, but you need to understand what you need to understand is that somehow they minimize these quantities right here. So, in what sense? So if I normalize, if I take the difference of the energy in the plus boundary condition with respect to the Hamiltonian calculated on sigma plus, this will give me sum of jxy 1 minus sigma x sigma y plus the sum jxy 1 minus sigma x. And notice that since this can only be at most plus 1, so this quantity right here can only be larger than 0. So this is larger than 0. This quantity right here is also larger than 0. So if I normalize by this quantity right here, then I always get something that is positive. So this is nice for me here, because since I have minus beta, if I manage to put this normalizing energy over there, then I will have a sum of exponentials that depends on a parameter beta, and this is nice. So using this trick, I can, by multiplying and dividing by the same thing, I can write this expectation here as 1 over exponential of beta h plus sigma plus times 1 that expectation over there times what? So you sum over all the configurations right here such that sigma 0 is minus 1, and then here I have minus beta sigma minus h plus sigma plus. Okay. So now this is nice. So another thing that I want to draw your attention to is to this term right here. So this term right here, you can show that it is actually always larger than 1. This term right here will always be larger than 1. Okay. So show this. So what happens is that I just need to see what happens to all the configurations that are here to this sum. Exponential minus h sigma lambda plus sigma plus. So what is this energy right here? So since we have a very special shape for the configuration energy, and since this Hamiltonian have a nice symmetry property with respect to the spin flip, what I know is the following. If the spins are different, okay, then this quantity right here will always be minus 1. And then I got for this term times 2. But if the spins are equal, for instance, deep inside the box, okay, this will give me they will have the same sign, and this quantity will be 0. Okay. So, and the same will happen right here. So inside something similar will happen there. If I am outside the box, the sign is plus 1, so that term will be 0. Okay, this term right here will be 0. And if I am inside the box, then this term will be 2. So what I have is plus will be equals to the sum of the pairs inside lambda such that they are an edge of the box. So x is inside the box and y is outside the box. Okay, so x is outside the box, jxy. And let us assume, for simplicity now, that we are in the nearest neighbor Ising model. Ising model. So plus the sum over x inside the box, y outside, j xy times 2. So what happens is the following. Since we are in the nearest neighbor Ising model, if I take a large box, a very large box, okay, a very large finite set here, finite set lambda, so the box is exactly container right here. So this means that for the nearest neighbor Ising model, this quantity right here will be 0. For the nearest neighbor Ising model, this quantity right here will be 0. So why? Center at some z. So why? Because the interaction with the box that are deep inside lambda with the outside would be long range. So, and then since now I am in the nearest, I'm assuming the nearest neighbor case, this will be the sum over what I call the edge boundary of the set, edge boundary of the box. Okay. Oh, 2 times j times the edge boundary of the box, where, remember the edge boundary, so the edge boundary is equal to the pairs, so the edge boundary of a set will be the pairs, all the pairs in ZD, so these are the, so these need to be edges, so are the pairs where the L1 distance is 1, such that x is inside lambda and y is outside lambda. So in this case right here, the edge boundary is something like this. And we only saw at some point the definition of inner boundary, but the edge boundary is comparable to the inner boundary, So show that the edge boundary is always larger than the inner boundary that we defined previously, and is less than 2 times the inner boundary. So yeah. What this means is that this quantity right here will always be larger than 2j times the inner boundary, and the inner boundary of a cube is just the quantity of numbers on its faces. Okay? So this will be Rd minus 1, approximately. And remember, for these configurations, we change it. We have a nice geometric picture, the cubes. And for a cube corresponding to a configuration to satisfy this constraint here, to sigma 0 to the sigma 0 be minus 1. So this means that the cube that corresponds to this configuration must be some translate of the cube centered at 0, such that this translate also contains the point 0. So configurations can be like this one. Oh, sorry. So if zeros is here, the configuration can be this one, but it can also be something like this. For a different R prime. So this can be another configuration. So what this means is that that sum over there will be less than if I divided this configuration by level sets according to the radius of the cube. And remember, the radius is always will be always an integer, so it's a sum. And then I need to count every translation of CR0 such that 0 is inside the translation. Times what? Times the energy that we saw. Is just a lower bound, is just an upper bound. So for an upper bound to the exponential minus beta, a lower bound is necessary. This will give me this. So this will be minus 2 beta j rd minus 1. Okay? And it's easy to see that all the translations of the cube will be exactly the points of the cube, each one of the points of the cube. So this means that the translations will be exactly the size of the volume of the cube, and the volume of the cube will be, well, the radius is always larger than 1, because at least one point is minus 1, sigma 0. So this will be this, exponential of the volume of the cube is the size r to the d, exponential of minus 2 beta j rd minus 1. So what happened is that I upper bounded every single one of these expectations here by a series that now doesn't depend on lambda. So it's uniform in lambda now. And by a manipulation, and by that I mean if I write r to the d as rd minus 1, 1 plus 1 over d minus 1, okay? If I write something like this, I can upper bound this series right here by a sum over all n larger than 1 of n 1 plus 1 over d minus 1 exponential of 2 beta j n. So you see, now I can take, since I start at 1 right here, this will be exponential of minus 2 beta j times a series starting at 0 now, exponential minus beta j n. Let me just change the index here. And this can be shown to converge. So this converges. And now I have bounded uniformly in lambda everything by a constant, something that converges, times exponential of minus 2 beta j. And j is positive. Remember, the system is ferromagnetic. So what happened is that I have a control here. So this quantity right here will be less than some constant times minus beta j. And in order to have, I already erased. So in order to have this quantity to be small, then I need to take beta large. And if I need to take beta large, this corresponds to a low temperature regime. So what is expected is that for the real system, remember, this is just, let's say, a hand wave, because I restricted my set of configurations to a very specific set of configurations. And what this made to the problem was to trivialize it, because now, let's say, the possibilities that I can see are small. They are at most polynomial in the radius, and this is not what happens in real life. Actually, for the general case, you have many more possibilities for configurations. And okay, but this is nice because this is it's like a testing ground to make conjectures about systems with competition. We will come back to this kind of toy model when we treat systems with a varying magnetic field, because in this case this will be nice to see how the competition goes in these easy configurations, and it allows us to conjecture the behavior of the real system when we drop that constraint. So, okay. Now we need to go to the direction to drop that constraint. So I will need a few definitions first. Okay, so remember that we gave ZD a graph structure, right? So remember that we are considering ZD as a graph, okay, as a graph. With the following, the vertex set are the points, just ZD, okay, and the edges, the set of all edges, again, are all the pairs, such that the L1 distance is equals to 1. So this will give us a grid. In graphs in general, in particular to ZD, we have a notion of connected sets. So, but the definition here, when I say connected, is path connected. So I said a subset lambda of ZD is said to be connected if for any 2 points there is a path connecting them. So what this means, if I have for instance, if I have Z2 and the nodes here of this grid are the points, okay? Then a path will be a set of edges such that the ending point of one of the edges is the starting point of the next one. So this is a path connecting Y to X. This is a path. Path connecting them inside lambda. So in order to be connected, any 2 points over here, for instance, if I define this lambda, over here, any 2 points inside this set right here, they can be connected by some path, as you can see, you can draw, okay? But for instance, this set here, so lambda prime, consisting of only 2 points is not connected. So you can see that these definitions make sense for any size of the subset. So you don't need to have any restriction. It don't need to be finite. So you can see that with this definition, Z2 and more generally ZD will always be connected. So for a given subset of ZD, a component, a subset lambda prime inside lambda is said to be maximally connected, okay, if for any subset right here in lambda such that lambda prime is connected, lambda 2 primes is connected, and 2 lambda prime is inside lambda 2 prime. So this will imply that lambda 2 prime is actually equal to lambda prime. So this means it is maximal with respect to the order given by, to the partial order given by the inclusion. So in this case right here, the only maximal for the orange lambda, the only maximal component is the whole set, okay? But in this case, lambda prime, there are 2 maximally connected components that corresponds to the points right here. Okay. So okay, what were the most important ingredients in the toy model that we saw, besides its simplification of the model? With that toy model, we managed to change a problem that was only talking about the configurations of the spin system, and we changed it to something that depends on geometries of subsets. In that case, the geometry was easy. The geometry was only cubes. So we are trying to mimic this property and to find the right geometric interpretation for the real system, the system with the configurations varying over all the local configuration space. So to make this connection, we will need another definition, and it's the following. Given a configuration, sigma here, with and a point on the lattice, okay, we say that x is plus correct. A similar definition for minus correct. If and only if the sign of the spin at the site y is equals to plus 1, respectively minus 1, for any y inside this set. For any y such that the distance to x in the L1 norm is less than 1. So what you will see, if here is your point x, then you will look to its nearest neighbors, okay? And then you check the signs. So if they all match, they are all equal. They are all equal. Then the point x is said to be plus correct. They are all equal, and they are all equal to plus 1. And minus correct if they are equal to minus 1. So, okay. And then, these are not the only two possibilities for a given configuration. If x is not plus or minus correct for sigma, then we call it incorrect. So for any configuration, we will write partial sigma as being the set of all x in ZD such that x is incorrect for sigma. So these are only the sites that are incorrect. So why this definition? Remember that locally, for instance, let us focus now on the case of the nearest neighbor Ising model, okay? So in this case, when I look to the system locally here, the energy in this box, the energy term in this box is something sigma x, sigma y, okay? And then you sum over all y x like this, okay? This is the energy term right here. So what is happening here is that you have, for a plus correct point, you have locally the ground state plus for everything. And in the minus case, you have locally the minus the ground state corresponding to minus everywhere. So the incorrect points then are just deviations of some ground state configuration. In the case, the plus or the minus. And you can see by this definition that I gave that sigma will be finite, will be a finite subset if and only if there exists a finite subset such that sigma is inside sigma plus or sigma minus. So what is happening is that the incorrect points characterize local deviations from the ground state of the system. Okay. So for now, since we are interested on the local configuration space with respect to the plus boundary condition, we will always assume now, for the remaining discussion, that the boundary of a configuration will always be finite. Okay. So, okay. What I need more? I need a couple more definitions on discrete geometry. So okay. So if lambda is a finite subset of ZD, lambda is a finite subset of ZD, so there exists only one. If you look to lambda c, there will exist only one subset here, maximally connected, and unbounded. So this means that its size is infinite. And it's easy to see because, okay, if this is your subset, then I can have some holes in the subset. If lambda is just the orange area right here, lambda is the orange area right here, then let's see the green one. When I look to the complement of the set, then the maximally connected components are just this square right here, this square right here, and the whole universe outside this box. And as you can see, there is only one maximally connected unbounded component. And if you don't believe me, you can try to prove it yourself. And you see that it's easy. So there is only one unbounded component. This unbounded component here is the green part, lambda prime. So what happens when I take the complement of this unbounded component? When I take the complement of this unbounded component, I will get something that contains lambda, okay, but does not necessarily equals to lambda. So what will happen? To this drawing over there. If I take the complement, then I will not only add lambda previously, the lambda that was already here, but I will also add all these holes that were inside lambda. So the complement will be the set lambda, but with no holes in it. And this is what I call the volume of lambda. This is the volume of lambda, and I denote it by V lambda. As the complement of the unique bounded unbounded component of the complement of lambda. Okay, so this definition only works now for finite sets. Okay, and I will call the interior, similarly the interior, and I will denote it by E lambda as being V lambda minus E lambda. Oh, sorry, V lambda minus lambda. So V lambda minus lambda, in the picture, what I would get? I would get these two quantities, these two, no, bad, not a good choice. So yellow. So I would get this and this as being the interior. There is also a similar, I can have another definition. I just take the union of all the maximally connected components, or similarly, I can take all or the union of all maximally connected finite components of lambda c, lambda the complement. This is exactly the holes, okay? So this definition will be important in what follows. Okay, now I have everything that I want. So the geometric objects that will make the role of the cubes in the toy model are called contours. So definition is, so a contour first I need a configuration. So given lambda, a contour given sigma, a contour is a pair C, sigma C is a pair like this, and I write it as gamma, so it's a pair where C is a maximally connected component of the boundary, okay? And sigma c is the restriction of the configuration at C. So a contour in this case will have two informations. One information is given by a geometric notion, a notion given with the help of the incorrect points, and also an information using the configurations. Okay. I decided to do like this because for cluster expansions the paper is with this definition, so I'll use like this. So, and hopefully we will get to cluster expansion in February. So, okay. But notice that not only geometric, there is not only a geometric information of the contours right here. There is also an information on the sign. So, and this is important because, as you can see, or better, as you can imagine, you can see in your head that if you have a general configuration, it's not true that the incorrect points will always give me a boundary set that is connected. This was something that happened on the toy model, but it's something that doesn't happen every time. So usually for a configuration you have many contours. You have a family of contours associated to a given configuration. And at some point in the argument, I also forgot what is happening to the system with regards to the configurations, and then at some point I just started to look to the geometry of the problem. But in this case right here, I have to take care because there's not only geometry, there is also configuration, so there is a sign over here. And what this means is that I cannot map every configuration to any given collection of contours. Why? Because what may happen is that if I have a given family of contours, there may also what can happen is that it can maybe there is no configuration that corresponds to that given family of contours. And to see this, I want you to first show another thing. That's the following. Show that. Okay. So show that sigma x show that sigma is constant at each connected component of the inner boundary of C. May not be, it can be not connected. It can be not connected. So, just an example. So suppose that your set C is something like this. So you have something like this. And then you have two holes right here. And the set is this orange region here. So this is your component C. The inner boundary of the set has as connected components. The inner boundary is something like this. So, can you see the difference between orange and yellow? Can you see the difference? No? Well, okay. So let me. Maybe green is better, right? Okay. So then the inner boundary is this green set here. But notice also that these two holes are contained in the exterior, so the inner boundary is also, it also contains these two sets right here. This is the inner boundary. This is the inner boundary. The inner boundary C. So what this exercise is asking is to show that in each one of these connected components, the sign is constant. It's not true that the sign will always be constant in the inner boundary. But it is true that if you look at each one of the connected components, the sign will need to be constant. And a way that you can imagine to convince yourself that this is actually true is to notice that C is a maximally connected component of the incorrect points. So this set contains all the points on sigma that you have some sort of change, of sign change. So if you go outside the set, okay, if you go outside the set, for instance, if your boundary configuration, if your boundary is just this set C, for instance, so if you go out, what this means is that all the incorrect points must be inside this region. All the incorrect points must be inside this region. So the only way that you can have, there is no way that you can have a change in the sign outside here, because otherwise, if you have a change in the sign outside here, then you would have another incorrect point, and this would not be a maximally connected component. Okay, so of course, in this case, because what happens is that in the general case, you can have another component inside here, for instance. But if you restrict the inner boundary, then you have the constancy of the spin configuration. So, okay. And all this information of the sign in the inner boundary is contained here in this configuration. And for instance, if you try to put another contour inside here to say, okay, I forgot another connected component inside here, C, but I know that the inner boundary of this set the inner boundary of this set inside here have a sign, let's say a plus sign, so sigma here in C prime, sigma in the inner boundary of C prime is always equals to plus, and here in this component, let's say that sigma x is always equals to -1. So what is happening is, since these components, these are all connected components of the incorrect points, this means that the complement of these sets, this means the black regions over here, must consist of correct points. If they are plus or minus, doesn't matter, but they need to be correct points. Actually, now it mattered, because what happens is, if I say that here I have a +1 and here I have a -1, this means that the only way that this can correspond to a configuration is that if there is some change of sign inside here. But in the black region, it cannot have a change of sign, because it's not a region containing the incorrect points. So these two, C prime and C, are not compatible. So they are a family of contours that, in the case, consisting of only two contours, that does not come from a configuration. Okay? So you need to take care of this stuff. So a family of contours gamma, let's say gamma 1, gamma n, is said to be compatible if and only if there is a configuration sigma such that the family of contours that this definition gives you, such that, and I will call it gamma sigma, big gamma sigma, is equal to gamma 1, gamma n. So this is the family of contours associated to a given configuration through this procedure here, by breaking the system in maximally connected components. So these are the geometric objects that substitute the cubes that we saw at the beginning of the class today. Okay. Okay, so yeah, I'll write like here. So for each sigma here, configuration, the local configuration space, you have the inner boundary. With the inner boundary, you can break it into maximally connected sets. So since this is a finite set, there is only a finite amount of maximally connected sets. Okay? So I say that gamma sigma is just the family of contours of C1, sigma C1, Cn, sigma Cn, Okay. So these pairs right here, the maximally connected component and this one, where C1, Cn are the maximally connected components of the boundary. Okay, so this is gamma sigma. But of course, a contour you can see just as a pair, a finite connected set, and some configuration on this finite set, and all the compatibility discussion happens because of this. Because what happens is that you want to see contours as objects on their own that doesn't depend on their family. Okay, but turns out that this is somewhat problematic, because when you do this, then you can have two or more contours that will not be compatible, in the sense that okay, in this case they will be connected, they will be compatible because they come from a configuration. But if I only see contours as give me a connected subset of ZD and a configuration of the set, if I give you only this, then it's not true that any two contours in this sense will have a configuration behind them, because sorry. Yeah. 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 Okay. It must be a configuration that such that every point is incorrect inside that component. You are right. But the phenomena of compatibility is also related to this problem. The problem that, since in this case you have an information on the configuration, I cannot take one component. What this means is that I cannot, for this given family, I cannot, for instance, erase one of these, okay, and say that there will correspond a configuration that has exactly this as the family. Well, what I mean in terms of equation is the following. It is not true that, for instance, that there always exists a configuration such that if I have that family over there, and for instance I take C1, it's not true that, so this as a set, it makes sense, okay, because this is just C2 to Cn. But it's not true that there will always be a configuration such that this set will be equal to the family of configurations of some configuration. And the problem that is happening is this one. When I try to erase one object over there, there will be some problems related to the regions where you have plus or minus correct points. For instance, another example where you can see this happening. let's say that your configuration is something like this. You have this component right here. This will be C1. And then you have another component inside. Right here. And then I have another thing right here. So the white part is the boundary of your set. There are three maximally connected sets. This one, C1, this one, C2, and one here, C3. Okay. So to have contours, I will also need to have the definition of contours. I will have to pick the configuration inside the white part. So the contours will be stuff like this. Okay? And remember, by the exercise, what happens is, okay, again, since this is the set of incorrect points, the complement of this set consists of only, the complement of this set right here consists of only correct points, or plus correct or minus correct points. So, for instance, no, yellow is not good, so green. So green, yeah. This green component is a region of correct points. Correct points. Side here, you also have correct points. Here, you will also have correct points. You also have correct points. And what is happening is, since they are correct, there cannot be a change in sign inside the green region. But between two green regions, since there is a change of sign here, because this is a region of incorrect points, this means that although these two regions are consists of only correct points, the signs here may differ from the signs here. Okay? So what happens when I try to erase? I have something inside here, and this will be C3 omega C3, such that omega C3 equals sigma C3. I want to know if I erase some contour in this set. Here I have three contours. So if I erase this contour on this set, then I want to know if I will have a corresponding configuration, omega, such that it matches, okay? It matches the configurations exactly at the previous points. Okay? So exists a configuration with here, also inside here, let's say, satisfying this. So, what is the problem? Suppose that in this region right here, this first region, I have a minus sign. So in this region right here, I know that they are always minus correct. But I know that outside, in this region right here, I know that this is a region of plus correct points. So what is happening is that since this is a region of incorrect, since this is a region of incorrect points right here, it allows me to change the sign here and the sign here. But if I pick this constraint right here, the configurations must match sigma C2 and sigma C3. What will give me is that, okay, not surprisingly, the sign of the inner boundary right here that I told you in the exercise that is constant, the sign of the inner boundary will be the same sign as this component right here. So in this example, since this is a minus correct component, this here will have a minus sign. This inner boundary here will also have a minus sign. So this means, in this case, that this will have a minus sign. This will have to be minus 1. Okay? And the configuration will always, in this, have to of being plus outside. But since I asked this, that the configuration inside C2 for omega must be exactly the configuration as sigma 2, I want that the configuration in the inner boundary should be minus. But outside, notice, outside there is no more incorrect region right here. The only correct regions are the white parts. So this means that outside this region, the sign should match the boundary. The sign should be correct, right? So they will always be equal, and they should match the sign of the boundary. So right outside here, I will always have a plus sign. But now I have a problem, because outside I have plus correct points, and at the inner boundary here I have minus points. So this means that right over here, right over this region here, I also will have a region of incorrect points. So these cannot be the maximally connected components. So this is the problem. Okay. I hope that now it is clear. You seem confused. Okay. So, okay. This is the problem with compatibility. So, let's see. So, we stop with the definition of contours today, and next class we will show how this definition behaves with respect to the energy. So, see you tomorrow. Diga.